All right. Last thing, ladies, whenever you're ready. Last thing for bonding models, molecular geometry. It's hammer time. No, okay. It really is. It's not like mathematical geometry. Molecular geometry is what a atom or a molecule looks like in real space. So you previously have learned how to do Lewis structures, which is drawing a two-dimensional representation of a three-dimensional thing. Now you're going to use those two-dimensional representations of three-dimensional things to imagine how that three-dimensional thing looks like in real space. Okay? And it's based upon the idea that electrons, whether they are unshared or bonding, repel each other. So if we were to draw water, we would remember that water is an oxygen, and oxygen has 1, 2, 3, 4, 5, 6 electrons. Right? Remember this? Yeah. Okay. And then hydrogen has, of course, 1 each. So when we bond the hydrogen, we're going to put a hydrogen there, and that gets that dot, and a hydrogen there, and there's that dot. Then we're going to convert those two bonding pairs into a stick, because everybody likes sticks. There's a stick, and there's a stick. And our Lewis structure for water is complete. Okay? Now, each of these pairs of electrons is referred to as a domain. A domain is like a region or an area. Okay? So there's some domains. This bonding pair is a domain. This bonding pair is a domain. This unshared pair is a domain. And this unshared pair is a domain. You can...
Wow.
What? There we go.
There you go.
Better? All right. So it's our water flower. Okay, it's a flower. Anyway, so each of those pairs of electrons is a domain. Whether it's a bonding pair, in the case of the stick between the hydrogen and the oxygen, or an unshared pair that oxygen keeps with itself. And those domains repel each other. Now understand, a Lewis structure is a two-dimensional representation of a three-dimensional thing. But you can think about it as what does it look like in 3 dimensions, which is why I gave you the modeling kits, so you can play with the modeling kits last time. Might want to get that, it might be your mom. Mom, stop texting me. The theory that allows us to determine what a molecule looks like in real space is called VSEPR, Vesper.
That's a gunning hot. What did you say?
Probably spelled with a Y though.
Yeah.
So the V, well, let's see if we can figure out what these variables are. You've actually written this down in your crossword. What do you think the VS is?
Virtual.
No. Virtual stupidity. Fair enough. In this class, maybe. EP. Here's a really easy one. What does EP refer to?
Electron proton.
Electron pairs. Good. Electron pairs. Because we have an electron pair here, an electron pair here, an electron pair here. And what do electron pairs do? They repel. And where do you find the electron pairs?
Right side.
Fair enough. Valence shell electron pair repulsion theory. So this basically can all be summed up. If you like to write words, then here's a bunch of words to write up. But if you want to sum it all up, you basically sum it up this way. Electron pairs are domains. Domains repel each other. That sums up all of Vesper. If you like to write words, then you can look at the video on your tube and write it all down again. But again, you can sum it all up with electron pairs make domains. Domains repel each other. Some of you are just bound and determined to write everything on the screen. Then when I click away in 10 seconds, you're like, no! Bring it back! I was taught in 5th grade to write everything you see.
Okay, not everyone went to school here.
I was taught in last week to write everything you see in English class. So anyway, it can all be summed up as all electron pairs create domains. And these domains are negative regions that repel each other. Now, when they do repel each other, they create some geometries. Okay, pretty simple. The simplest geometry is if you had two friends and those friends hated each other, but they liked you, where would those friends go?
To me.
On the opposite sides, right? So there's friend A, there's friend B. They hate each other, but they like you, so they orientate themselves as far away as possible, and that creates a linear geometry.
Can you say that all electron pairs?
Yes?
So all electron pairs are domains.
And domains repel, because electrons repel.
So on that one, the H on the left side and the dots on the right side repel each other, but they're attracted to the oxygen.
Exactly. So if you didn't hear because you were chatting on your own with your own thing, so the question was, so the H's repel each other, but they're attracted to the oxygen. That's exactly what's going on. So the central atom, the domains are attached to the central atom, but they repel each other. This hydrogen repels this hydrogen's domain. This hydrogen's domain repels this unshared pair domain. This unshared pair domain repels that unshared domain. And because of that, they create a shape that looks like this. This is a tetrahedron. You imagine water molecule with a domain and a domain and domain, domain. 4 domains repelling each other creates a 4-sided shape called a tetrahedron. Now these are the 5 fundamental domains. If you have 2 domains attached to a central atom, you get a linear configuration. It's linear. If you have 3 domains connected to a central atom, here's the linear, you get a triangle in a plane, like the Mercedes symbol, where they want to get as far away from each other as possible, so they'll orientate themselves at 120 degrees in a plane. It's called trigonal planar. That's the adjective of triangle in a plane. Now on a test, you will be required to, just like before, draw the Lewis structure of an atom, determine its polarity, draw the dipole if it's polar, write nonpolar if it's not, and then now identify its geometry. So if you write trigonal planar, yay. If you write triangle in a plane, that's fine too. Okay? I'm not going to worry too much about it. Understand that these will be open-ended and you will actually need to write down. I'm not going to ask you, identify the triangle. Which one's a triangle? No, it's all going to be open-ended. You'll have to write down trigonal planar, linear, or whatever. Okay, if you have 4 domains, those 4 domains will orientate themselves in a tetrahedron, a tetrahedral geometry. They will get as far away from each other as they can, and in real space, that's about 110 degrees away from each other. Yeah?
Does one tetrahedral always have 5 atoms?
Yep. Well, okay, no. We're talking about the fundamental geometries now. We'll talk about atoms versus, we'll talk about bonding pairs versus unshared pairs in a little bit. But yeah, to have a tetrahedral, you'll have to have 4 domains connected to a central thing. Okay. Remember, remember Tetris? That dun, 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 dun. So the reason it was called Tetris is because you can make 4 lines. A tetra. We'll talk about tetra later on when we name molecules. Now, if you have 5 domains, something kind of interesting happens. I drilled holes in our molecular models yesterday. If you have 5 domains, then you get what's called a trigonal bipyramidal configuration, where you have 3 in the triangle plane, and then you have a 4th and a 5th above and below it. So it makes a triangle pyramid above a triangle pyramid. So there's a triangle pyramid, and down here's a triangle pyramid. Trigonal bipyramidal, where you have 3 in a plane, and then 1 and 2 above and below it. Pretty slick little deal. Okay. That's if you have 5. Now if you have 6, it's kind of cool. It's not called hexahedral, it's called octahedral, because if you have 6 domains, you have a square pyramid on top and a square pyramid down below. It's an octahedron.
Whoa.
It's an 8-sided shape.
That's cool.
Yeah. So 6-sided, you have 4 in a plane, 1 above and 1 below. That's an octahedron. Again, this is what it would look like if you had 6 domains all trying to get away from each other, but connected to the central atom. Octahedral. Okay, I'm going to leave these up here. The trigonal bipyramidal falls out a little bit sometimes because I made the hole too big. But yeah, there you go. That's what the hammer was for. Making holes. Hammers are good for making holes. Okay, so these are the fundamental domains. These are the domains when all you care about are the these are the geometries when all you care about are the domains. Now, below each fundamental domain, after linear, there are subdomains, or below each geometry, below linear, there are subgeometries called molecular geometries. And we're going to learn those. You need to know what the molecular geometries are for 2, 3, and 4, but I'm not worrying about for 5 or 6. So, if you had 3 domains and all of them were bonding, your molecular geometry would also be trigonal planar. So if you had 3 domains overall, your fundamental geometry is trigonal planar. If all of those geometries, or all those domains, were bonding, then your molecular geometry, the geometry of your molecule, would also be trigonal planar. Like that. However, if one of those domains was unshared, your geometry then becomes bent. It's bent. So all 3 bonding, your molecular geometry is trigonal planar. One of them unshared, your molecular geometry is bent. Can you see the difference?
Well, why does it not show the third domain?
Because when we talk about molecular geometry, we only care about the geometry of the molecule. We don't care about the invisible unshared pairs. Now, the invisible unshared pairs are a domain. They are resisting or repelling the bonding domains, but we don't show them in the molecule. Does that idea make sense? A little bit? Maybe? Okay. So if all of them are bonding, your molecular geometry is going to be trigonal planar. If one of them is unshared, your molecular geometry is going to be bent. Like a boomerang. Okay? Okie dokie. Artichoke. Are we ready to move on? Okay. Now, if you have 4 domains, and all of those domains are bonding, then your molecular geometry will be tetrahedral, just like your fundamental geometry. So if you have 4 domains, no matter what they are, the fundamental geometry is tetrahedral. If all of those domains are bonding, your molecular geometry will also be tetrahedral, which is what we get with methane. You made methane in your modeling lab, where you got the carbon in the middle and 4 hydrogens on around the outside. Okay. If one of those domains is not bonding, if one of those domains is unshared, what you get is trigonal pyramidal, triangle pyramid. So ammonia, you drew ammonia, you built ammonia. Ammonia has an unshared pair above the nitrogen, but the hydrogens are still domains. Those unshared pairs push the hydrogen domains down, and what you get is a trigonal pyramidal configuration. If you say triangle pyramid, that's okay. Okay. Trigonal pyramidal, tetrahedral. Can you see the difference? It's the dance of the molecules. Yeah.
The difference is just like that there's 4 domains, and when it's a trigonal pyramidal, it's just that one of the domains like is unshared, so it doesn't want to bond.
It doesn't bond because it's unshared. It stays with the nitrogen. But it's still a domain. It's that invisible unshared pair domain that still pushes the hydrogen bonding domains down. It's still there, but you don't see it in the molecule. Does that make sense?
Yeah.
Okay. Any other questions about that? All right. If half of your domains are bonding and half of them are unshared, then you get bent. So here's your tetrahedral, and here's your bent molecule. Water molecule is a bent molecule. So the bent molecule, you've got 2 bonding domains and 2 unshared domains. So when we look at our diagram here, the fundamental geometry is tetrahedral. But the molecular geometry, the geometry we actually care about, is bent. Which is why water molecules are boomerang shaped. It's a boomerang shaped molecule of water!
Is that the same as CO2?
No.
Do they have like that double bond thing?
Yeah, CO2, since you brought it up, I'll go ahead and draw it. CO2 has our carbon in the middle and then 2 bonded oxygens. And then the oxygens have a pair of unshared pair electrons. So you only have 2 domains here. You have this domain and this domain. So this is linear.
But isn't
The oxygen's unshared pairs would be domains around the oxygen. But in this class, we're just going to focus upon the geometry around a central atom.
around the center? So it doesn't matter how many like electron pairs are around the outside atom?
No. Again, we can get more complicated, and computers do. We can use computers to get really complicated. Right now, we're just going to focus on the geometry around a central atom. If you want to learn how to make medications or protein folding, you can learn that in your junior or senior year in college and learn about really exotic geometries. We're just going to focus on the fundamental, simple geometries. Okay, questions? We are almost done. For 5 and 6, there's a lot of molecular geometries. We're not going to worry about them. All we're going to care about for 5 and 6 is if you see 5 domains, it's trigonal pyramidal. If you're curious what the other ones are, you don't need to write this down, but the other ones are seesaw, T-shaped, and linear. But again, if you see 5 domains, in this class, we're just going to focus on they're all bonding. 5 domains, all bonding, would be trigonal bipyramidal. Triangle, pyramid, triangle, pyramid, triangle, pyramid, on top of triangle, pyramid, triangle, pyramid, triangle, pyramid. And again, 6 domains, octahedral. And there's a whole bunch more for octahedral too. But we're not going to learn those. All we care about is if you have 6 domains, you have a 1, 2, 3, 4-sided pyramid above a 1, 2, 3, 4-sided pyramid. That's an octahedron. Octahedron. Octahedral. If you're curious what the other ones are, square pyramidal, square planar, and there's one called T-shape and seesaw, and yeah, we're not going to care about those. Okay, questions? Do you want to see a video or skip a little video? It's like a 3-minute video. Watch the video. Okay, skip back, and after the video, we'll do the practice. Hey, come back, video. Where'd you go? There you are.
The electron pairs that surround the central atom are most likely to be found in confined regions of space called electron domains. The arrangement of the electron domains about a central atom are determined by electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time they are held by their attraction for the central atom. When there are 2 electron domains about a central atom, They are located 180 degrees apart to minimize repulsion. 3 electron domains about the central atom take up positions in a plane separated by 120 degrees. 4 electron domains form a tetrahedral arrangement about the central atom. 5 electron domains form a trigonal bipyramidal arrangement. 2 of the electron domains are disposed along the vertical axis. The other 3 are found in the horizontal plane, separated by 120-degree angles. 6 electron domains are located along the X, Y, and Z axes at 90 degrees from one another. This arrangement is termed octahedral.
All right, so with what you now know, I would like you to practice on your own these. HCl, NH3, CCl4, CH3Cl, and BF3. What I'd like you to do is, on your paper, draw the Lewis structures. Hey, come back. Oh, okay, here we go. Draw the Lewis structures, determine their geometry, determine their polarity, and then compare it with your neighbor. Again, this is what you're going to have to do on the test at the end of the week, is you're going to have to draw the Lewis structures, determine polarity like you've been doing, and now also determine their molecular geometry.